So as you dive into MP2 and we build this triangle rasterizer, you'll notice there's a lot more math involved. And it's not math that we can't handle, but as we implement that math in hardware, one thing you'll catch on to pretty quickly is we do have to have this extra level of awareness of the data types we're using and why we're using those particular data types. So I thought for this sort of lab introductory video, I'd walk through a little bit more carefully our data types, how we're representing things, and how you can use that as you're building the architecture for the triangle rasterizer. If you look in the MP1 or MP2 repository in the IP subdirectory for our hardware, the first thing you'll see is that sort of standalone file, that SGP underscore types.vhd. I include this file for you outside of anything that's in a directory because it's shared amongst a lot of those cores. Vivado doesn't actually like that you do that, and so if you're seeing that you're having some problems where it can't find this file, well, we're not changing this file all that much, so feel free just to copy it to one of those local directories. But the idea was that it's a single file, it's shared amongst a lot of different IP cores. And for the most part, this is storing our data types that we have here. You already used this a little bit in MP1, but now we really, I think, need to truly understand it to be successful in MP2. Starts off with some constant declarations for the primitive assembly you're doing in this assignment. I don't think you'll find that state machine too hard, so I'm not going to belabor that right now. The next thing it defines are some constants with regards to what is each vertex in terms of the number of attributes that comprise a vertex and then the size of each of those attributes. Now, this is not to OpenGL spec. OpenGL specs states that there's going to be some per implementation constant for the number of maximum vertex attributes, and each vertex could have between one and that maximum number of vertex attributes, and they can be of varying sizes. We could have also implemented it exactly like that. That would have made our logic for storing vertices, for fetching them, and for kind of passing them along the pipeline a lot messier than it is in its current incarnation. So I made the early design decision to say we're going to have 4 attributes, not maximum, not minimum, always 4 attributes per vertex. They're filled with zeros if we're not using them for anything. And then each attribute is also going to be a 4 wide vector. And that's what these first 2 constants are indicating here. That each vertex has 4 attributes, and then there's 4 dimensions, or it's a vector of size 4 per attribute. And having that visualized as you're looking at data flowing through the pipeline, I think will be helpful. So just think of it as there being just this 4 size array of 4 things. So we'll draw that to get started, and then we'll kind of fill in those details here. So you would have that first attribute. That would be a 4-element array. Same with your second. We're going to run out a little bit of space here. So we'll zoom out. Got one too many here. And then finally, our 4th element in that array. I would also add that the OpenGL spec doesn't necessarily say exactly which of those attributes are for which purpose, and you have to encode it in your shader specifically which one is going to correspond to color or positional data. And we also don't have that limitation as well. As you will see as you look at data being fetched, we do make the fundamental assumption, and your MP1 code took this into account as you were doing your render output module, that the very first attribute, we'll call that attribute 0 here, is going to be storing your position data. And specifically, it's going to be storing your X, Y, Z, W data. And also, what's hard-coded into our pipeline based on how you wrote your render output, attribute 1 is going to be always our color data. Whether we specify color as part of the vertex as we send it, or if we generate the color through something that's happening in the shader, we want to always be putting that in attribute location 1. We could call that XYZW. Oftentimes it's easier to think about color as being RGBA. And our attributes are not overlapping each other, but the same principle is still valid here. And then the other 2 are just kind of placeholders. Whatever you need 2 other attributes for, vector normals, texture coordinates, there, at least as of right now, as we look at MP2, there's nothing that's requiring that attribute be put in a particular location. But for the first two, it is fixed. We already had to take that into account for MP1. To do your viewport, it had to know where the position was. To do your render output, it had to know which one was the color and to take that information together to be able to store a value in the frame buffer. And we're still following that approach for this MP2 assignment. So when we look at our data types, we start with those constants that define how large our data type in terms of the vertex attribute is going to be. And then separately we then have this fixed point data type. I spent a little bit of time in MP1 talking about that. This Q16.16 format, if we look at how it's defined in our VHDL package here, there's nothing interesting especially happening here. I'm just saying I want 16 bits dedicated to the integer component and 16 bits dedicated to the fractional component. And so when I look at that data type, it's just specifying it as a signed array. And the reason we can do that, again, is that's the whole point of fixed point. We can do integer math and get some fractional values that allow us to store things like 1.25 with just a couple of additional bits for those fractional components there. So in terms of the data type from the VHDL perspective, from our operators we're doing to do our triangle rasterizer, it's an integer. It's an integer of length 32. We then just have to keep track of the fact that actually 16 of those bits are integer, representing the integer, those positive powers of 2, and then those other 16 bits are representing the fractional powers of 2. But the actual data type is just a 32 length signed, which is again just our standard logic vectors here. It can be helpful to have, to initialize things as opposed to worrying about exactly how you initialize something to 0 or how to initialize something to 1. I just have those defined as constants. That is 1 in our Q16.16 format, and 0 is still just 0. That's our Q16.16 data type. We know even from back in MP0 what happens when we multiply those two of those values together. Take a 32-bit value, multiply it by another 32-bit value. If you don't want to lose any information, you need a 64-bit result to store that result. And that's the same in our fixed point format as well. If you take a Q16.16 and multiply it by another Q16.16, if you don't want to either overflow or potentially underflow that value, you need a Q32.32 to hold all that information. So if we have this fixed T subtype is a 32-bit int, our W fixed T for wide fixed point data type is a Q32.32. It's a 64 bit integer here. The syntax is just trying to look a little clever here and saying, well, take the length of the previous one and double it. We could have done 2 times C SGP integer bits plus 2 times C fixed bits. It would have given you the same result. This is fixed length is 32, so this gives us 63 down to 0. And finally, you may find some circumstances in which you are taking the multiplication of 2 fixed point values for your rasterizer and then multiplying it by an additional value. These multipliers are starting to get pretty wide, and we have to be careful when we use them. But in order to have that, you would then have what I not so cleverly call a WW fixed, a really wide fixed point type. That's our 64-bit data type. That's to store the result of a 32.32 values multiplied by each other. So that's the fixed point type. And while OpenGL doesn't require this to be the case, our implementation to keep our both driver and our hardware implementation as straightforward as possible is specifying that for each of these values we have in the attribute, each of these is going to be that Q16.16. Even though, while some have already mentioned, for color, it's often more natural to define things as an integer value, and we have to convert it ultimately anyway. In terms of how we take the attributes specified in our OpenGL and how we send them through into our pipeline via the vertex fetch unit, those are all going to be those Q16.16 values. There's other approaches we could take. You just would have to write a driver pass that can handle those values. For now, everything is Q16.16. So when we think about these attributes, we can take all this information and combine it together. We have 4 attributes, each of which have basically a 4-wide vector. And each of these elements inside that 4-wide vector for each of these attributes is a Q 16.16. So 32, 64, 96. Each of these individual attributes then is 128 bits. And as you've already seen, even when working with just with MP0, well, now we can have a 512-bit data type working with that array, indexing the right and subslicing the right values out of that array can get messy pretty quickly. At least in my opinion, that's the case. There's a lot of completely valid but horribly illegible VHDL array indexing math I saw in MP0 designs that you submitted. This package is an attempt to try to minimize the amount of that you have to do in your code. I have done it all for you once, so just use this package versus having to worry about it yourself. So we start with the definition of what the attribute then looks like. For an individual attribute, that's 4 of those fixed point data types, and that's what this first subtype is attempting to be. I call it an attribute vector. Um, the corollary there is to the standard logic vector. It's a vector type that stores an attribute value. So it's 4 size of each attribute times the size of fixed length. It's a big long 128-bit signed array. I also then define a type that instead of accessing this entire array as one large standard logic vector or signed vector, that's going to make your code really awful. You're going to have to constantly remember which one was X, which one was Y, which one was Z, indexing in little for loops just scattered throughout your code. I also create a type that then takes that value and defines it instead as an array. Yes, I know a vector and an array in VHDL are kind of synonymous terms here, but in this case, it's an array of those fixed types. It's the same number of total bits. This is a single 128-bit array. This is an array of 4 elements of 32 bits each. So it's the same storage, and it has to be the same amount of storage. But in this case now, you can access it via attribute of 0, attribute of 1, attribute of 2, an attribute of 3, and get back out just a single fixed T type. That's going to make your code a lot cleaner if you use that. And then separately, there's an additional type that if you like to think of things in terms of variables in your code, this may be easier to work with, in which I just define a record type in VHDL. Think of it like a struct in RC, in which the attribute now is an XYZW. I could have called it RGBA or RSTU and things like that. But for now, XYZW is sufficiently descriptive for that. It's still the same amount of storage. It's 4 of those fixed T data types. It's still a 128-bit data type. It's equivalent one to the other, vector array to record here. It's up to you which one you feel is easiest to work with. When defining a FIFO, where we know that there's just a single bit array as the interface of our FIFO, using the vector type is going to be the way to do it. But now when I actually want to do some processing on those data types, you're going to find that the array subtype or the record subtype is going to make life, I believe, a lot easier for you. And then there's these functions that are just defined to convert from one to the other. Just look at the package. You can see what that requires. If I want to go to an array type from the vector type, we can find the code for that down here somewhere. To array from the vector type is defined down here. And it's exactly the kind of for loops that you'd have to have scattered throughout your code if you were doing this a lot in your own modules. Use that function. It'll synthesize just as well. It's as if you would copy pasted this code multiple times into your code. So just use this one instead. It'll make your life a lot easier. And there's conversion functions between all those different types. And similarly, although you could also do this yourself, conversion functions between the wide fixed to the fixed and the fixed to the wide fixed, so that if you get a 64-bit result and your analysis, your paper and pencil tells you, I actually really only want a 16.16 result of this multiplication. Yes, you could do it yourself, or hey, here is a function that does it for you. Just use it. It'll synthesize. It does exactly what you would expect it to do. Grab just those inner 32 bits of that 64-bit value to truncate both the high-order integer bits and the low-order fractional bits to get the value back out. And then finally, I think you're getting the idea of what I was going for with this. That is for our attribute vector array and record type. We also then, to make sure we have our FIFO interface, we're going to be passing these 512-bit values down the pipeline, keeping track of what is equally difficult as it is in the individual attribute case. We then finally have that final data type whose job is to just store all the values associated with that vertex. So the math is still valid. Take the number of vertex attributes times the size of that attribute vector We could have done 4 times 4 times 32. In this case, we do 4 times 128, 512-bit vector there, and now have what will now be a multi-dimensional array data type and a multi-dimensional structured data type to be able to access those values. I want, if I wanted, of my input vector, of my input vertex, I want array attribute 0, sub value 0. I can use this vertex array type and grab that in one very clean looking line of code, get the 32-bit value I'm expecting back out. With conversion functions in for them, in theory, I could have created n cross m different data types here, but in practice, what I just have is the really wide 512-bit vector, the 3 by 3 array type, and then the two-dimensional record type as well, with conversion functions defined between those. There's really no reason to use array versus record. It's whatever you're more comfortable with as you're working in the code. It's equivalent. It's the same exact amount of logic. It doesn't lead to one additional gate using one of these types versus the other. Um, in my experience so far, for my interfaces for things, having those vectors makes a lot of sense because then I can hook it up to a FIFO and things that don't have any knowledge of this data type at all. But then doing the actual math, I was able to keep track of things pretty easily by having these array types. And I can iterate through an array a lot cleaner than trying to subslice out a really wide vector. And the record was a nice idea, but led to more lines of code, I guess. I couldn't wrap things in for loops that I otherwise would have wanted to with those vector types. And since you do know that we're doing primitive assembly and then finally triangle rasterization, the actual triangle itself then is also a useful data type for us to have. So this individual vertex types are good for storing a single vertex, but we know a triangle is 3 vertices. And so that's all that this triangle array is doing here. This triangle array is just an array of 3 of those vertex types. And that's a very useful thing to have. You can then convert the individual vertices inside that triangle type and then convert the individual attributes within that entire vertex type. But something to keep in mind as you design this component for MP2, and part of the reason that doing things like meeting timing can be tricky in MP2, well, this is a 512-bit vertex vector. That's a single vertex. We're going to have 3 of them for your triangle type that you're going to want to be passing these triangles around in your design here. That is a very wide bus. And when you have such a very wide bus, you do have to be a little bit more careful that with all those wires and routing all those wires, how do you ensure that you're actually meeting timing? You're likely going to run into that for MP2. But I think you're going to have a lot of fun with working on this design. You're going to finally get to see some, I think, realer looking applications running on the board at the end of this assignment. So get started on that. Look at that package. Have that package file just kind of handy to look at to know what functions are there. And if you find yourself writing a really lot of low level looking data conversion code in your modules, maybe step back briefly and say, well, it's probably already there. Let me use the one that's provided for me because it should work. It's been reasonably well tested already. Otherwise, good luck, and I'm looking forward to seeing what you come up with MP2.